Hello and welcome back to the course on applied thermodynamics. Let's continue our study on vapor powered cycles. In today's lecture we are going to look at a new chart that is called as Mollier chart, or it is also called as Mollier diagram. We are going to look at how this Mollier chart is constructed and what kind of data one can extract based on Mollier chart, and we can also see what are the applications which are based on Mollier chart. Now to begin with, Mollier chart is also popularly called as HS plot. So it is a HS diagram or HS plot. Along the x-axis we are going to have entropy in kilojoule per kg Kelvin, and along y-axis we are going to have enthalpy in kilojoule per kg basis, and it is used to find out the properties of the working fluid. The working fluid can be steam or it can be refrigerant, and what kind of data one can extract from this HS plot is one can know the enthalpy at a given state point. One can also find out what is the entropy of the system at a given state point. Similarly, the specific volume at a given state point of the system, and the dryness fraction of the system if it is lying within the saturation dome especially, and also it can give us the temperature of the thermodynamic system at a given state point. So now let us look at the HS plot, how exactly it looks at. So here we have HS plot. So we have entropy along x-axis in kilojoule per kg Kelvin basis, then along y-axis we have enthalpy in kilojoule per kg basis, and we see that at origin, that is 0, 0, the curve proceeds, and what we see here is a dark thick curve, and this is the saturation dome. This is the saturation dome, and we know that the saturation dome is made up of two curves. One half of the curve is composed from saturated liquid curve, which I am pointing out here. This is on the left side of the dome, and we see that at the peak on a TS plot on a saturation dome, that point is called as a critical point. So here we have a critical point, and then the next half of the curve for the saturation dome is composed of saturated vapor curve, so which is shown here through this curve. So we have basically a saturated liquid curve, then we have a critical point, and then we have saturated vapor curve. And we know that the dryness fraction, which is the amount of steam that is present inside the system, will be 0 at the saturated liquid point. And then as we proceed by the absorption of latent heat, we are going to pass through the two-phase region and reach the saturated vapor curve. At this point the steam is dry saturated, therefore the dryness fraction will be 100% or 1. And as we come into the saturation dome, we know the quality is going to drop, amount of steam will start reducing, therefore we have 90%. And then if we move further into the saturation dome, we have 80%. Likewise we have 70%, 60, and all the way up to 0%. So this is about some information that we can get within the saturation dome. And then we also see that we have some pink data points here, pink data points. These are pointing out to the temperature at the corresponding state points or dots. So we see that it is 423 Kelvin, and likewise as we move to the critical point, so we have temperature in terms of Kelvin here, 647.3, and whatever the plot we are seeing, this is applicable for the water, that is for steam. Therefore the critical properties for water is been put up here, and then we see that the pink dots follows on the saturated vapor curve also. So now let's see what are the different curves that we can observe on this HS plot. We see that all the curves are originating almost near the origin. So we can see there are some blue dotted curves, and we also see there are dotted red curves, and we also see that there are some pink curves. So we have blue dotted curves, we have red dotted curves, and we also have some pink dotted curves. And the curves which are blue, these signifies or indicates the pressures existing along these curves. So we see that the pressure is varying from 0.01 bar and then all the way 0.1 bar, 1 bar, then we have 10 bar, 100 bar, likewise then we have 600 bar, and all the way up to 1000 bar. And we see that clearly in between some data is not shown here, but we can find it out based on interpolation. Therefore we see that the pressure is varying from 0.01 bar and all the way up to 1000 bar. Likewise, the dotted red curves indicates the specific volume, which we can see here, and these dotted red curves pass through the saturation dome and then they proceed way outside the dome, and this is a superheated region. And then we see that we have specific volume here, which is 100 meter cube per kg, then we have 20 meter cube per kg, likewise we have 10, then 2 and 1, 0.2, 0.1, then 0.02 meter cube per kg, and all the way up to 0.01 meter cube per kg. Again, in between these values data is not shown, but we can interpolate and get the value if we are interested in between. Likewise, we can also see that there are some temperature data here available. So for the clarity purpose, I think it is better to zoom this part so that we can find out clearly where are these dotted blue curves and dotted red curves, and along with the temperatures are shown. So let us zoom this part which is outside the saturation dome. So let's now zoom it. So we see that once we zoom that part on outside the dome, so here we have a saturation dome, and this is the saturated vapor curve along which the dryness fraction is 100%, and above this we have superheated region, and then we see the clearly the dotted blue curves, they indicate pressure, they indicate the pressure. For example, this particular curve, it indicates pressure as 10 bars, so the pressure is varying from 0.01 and all the way up to 1000 bar. Likewise, we can see the specific volume here, dotted red lines starting from 100 meter cube per kg and all the way up to 0.01 meter cube per kg. This is a specific volume variation. Likewise, we can also see the pink dots here, and at this point the temperature is 323 Kelvin, and once we drop a horizontal line towards the y-axis at this point, we see that the temperature is somewhere around here 0, and the next point here shown as 100 degrees Celsius, then we have 200 degrees Celsius, 300 degrees Celsius, and likewise all the way up to 800 degrees Celsius. But if we are interested at this point, then one can drop an horizontal line here, and if this is 0 and this is 100 degrees Celsius, this is approximately in between, therefore it can be read as 50 degrees Celsius. Likewise, in between data can be interpolated and can be worked out accordingly. So this is about the exaggerated view about the HS plot, where we can see the details pertaining to pressures, details pertaining to the specific volumes and the temperatures. Likewise, when we look at the y-axis, we have enthalpy, and we see that enthalpy is varying from 0 and all the way up to 5000 kilojoule per kg, and entropy is varying from 0 to all the way up to 12.5 kilojoule per kg Kelvin. Now let's proceed by taking one example to demonstrate how exactly one can interpret the data from the Mollier diagram. To do that, I have picked up one modified HS plot. So the modified HS plot has been shown here, where we have on x-axis we have entropy in kilojoule per kg Kelvin basis, and along y-axis we have enthalpy in kilojoule per kg basis. And then we can see clearly the saturation dome. This is saturated vapor line, this is, along which the dryness fraction is 100%, and we see the pressure curves starting from 0.01 bar and all the way up to, we can see it is up to 500 bar been shown here. Likewise, the temperatures also been shown here from 50 degrees Celsius and all the way up to 800 degrees Celsius. So we see there are green horizontal lines. These are constant temperature curves. Constant temperature curves. However, specific volume is not shown here. Now let us consider one problem where we have an isentropic expansion process happening, maybe typically in turbine. So we have state 1 data and state 2 data here. The system is existing at a pressure of 50 bar and at a temperature of 400 degrees Celsius, and it goes through isentropic expansion process in a turbine, and then it will arrive at a pressure of 1.9 bar. And with this given data, they asked us to find out what will be the change in enthalpy and what will be the entropy, and one can also find out the specific volume and the dryness fraction if required. So let's now locate the state points. Now, since the state point 1 is 50 bar and 400 degrees Celsius, from this curve we know that 50 bar curve is somewhere here as we proceed, and then 400 degrees Celsius is somewhere here. So 50 bar and 400 degrees Celsius, so the curve comes out somewhere here. So this will be the state point 1, where we have 50 bar pressure curve intersecting with 400 degree temperature curve. So this is a point where system is existing at state point 1. Now from this point, let us draw one horizontal line towards the y-axis. Then at this point we are going to pick up enthalpy value. So the enthalpy value, if this is 3000 and the next one is 3500, then in between we have a division of 100 kilojoule per kg. Therefore, if this is 3000, then this is 3100. Likewise, the point where our system is existing is 3200 kilojoule per kg. Likewise, now after the state point 1, the system is going through isentropic expansion, and we know that isentropic expansion is a process where the entropy remains constant, and we see that on the x-axis we have entropy. Therefore the system is now heading vertically downward direction, and they given us the pressure is 1.9 bar. Now let us look at the pressure curves here, where we have 0.01 bar, 0.02 bar, likewise 0.1 bar, 0.5 bar, then 1 bar, then we have 2 bar. But the given pressure at state point 2 is 1.9 bar. That means it is very close to 2 bar. So let's hold this pressure curve and follow through closer by to this point, because it is isentropically expanded Therefore we have the system existing just below this curve at this point. So at this point one can extend the line and cut the x-axis. Therefore we are going to pick up the entropy value at this point. Since it is isentropic expansion, then S1 will be equal to S2, and if you look into the data on the extreme ends, on one end we have 6.5, the other end we have 7, so therefore the increment is of the order of 0.2. Therefore it is around 6.7 kilojoule per kg Kelvin. So we have S1 is equal to S2, which is 6.7 kilojoule per kg Kelvin. Since this is a graphical representation, finding out the exact pinpoint value may not be possible, but in case of steam tables one can find out the exact value based upon interpolation. Since this is a graphical method, we can approximately figure out the state point where the system is existing. Now we have found out H1 and we have found out S1 and S2. Likewise at state point 2, if we draw one horizontal line towards the y-axis, we get enthalpy at state point 2 as 2500 kilojoule per kg. Therefore we have a system here undergoing expansion process where heat is rejected or heat is absorbed. Heat is rejected in fact. So therefore we have H1 minus H2. It is used, the difference in H1 minus H2. This is H2. Please make a note of this. This is H2. This can be interpreted as the amount of change in enthalpy has gone in producing the turbine work. Therefore friends, if we are interested to find out the dryness fraction at state point 1, then at state point 1, since it is superheated zone, we don't have dryness fraction being defined here, therefore this is omitted out. And at state point 2, since the state point 2 is well within the saturation dome, therefore dryness fraction is defined here. So at this point we can see that we have a saturation dome which is having dryness fraction 100%, and then we have the next red curve here which is showing 95%, and then we have the other one is 90%, but the state point what we have is just above 90%, so we can read this as 0.92 as dryness fraction or 92%. So likewise we can get a data related to enthalpies, we can get data related to entropies, and also we can get a data related to dryness fraction. And also we can find out what will be the specific volume if we would have had the curves here extending. One can find out specific volume also, which is shown here, can be found a specific volume. Similarly one can find out the temperature at this point if we would have had temperature scales. So friends, with this we are now comfortable in using HS plot. So when a question is asked in examination related to vapor powered cycle, and if the examiner asks to use HS plot, so this is a method one can use to find out the required properties of the working fluid. So friends, with this we have come to the end of today's lecture. Before that, let us look at the applications based on HS plot. The Mollier diagram or HS plot is popularly used in the design of steam turbines, or it can be used in air conditioning systems, refrigeration systems, and likewise the compressors as well. So friends, with this we have come to the end. Thank you for your attention.